All right, everyone. In this video, we are going to talk about two special kinds of line integrals, circulation and flux. And we have the definition of each of these written up on the screen right now. So each of these involves two things, a vector field, capital F, and a closed curve, gamma. And so when I say we have a closed curve, what I mean by that is that whatever our curve looks like, if it crosses itself, it's going to close off so that the one endpoint is the same as the other endpoint under a parameterization. So it does not have two endpoints per se, but it loops around like this. And if we were to parameterize it on an interval of time from A to B, then the endpoint we would get at time A and the endpoint we get at time B exist in the same point in space. So our classic example might be a circle, and more broadly, we tend to think of these. I drew that first one with self-intersections, but when I think about these in general, I tend to think of them maybe like this. So this might be called not just a closed curve, but a simple closed curve. It does not have any self-intersections. So when we have a closed curve gamma, it loops around like this and encloses a region of space. And I should also say that our space in this case is always going to be R2. That's going to be true for both of these definitions. So the curve that we're looking at is going to be a closed curve in two-dimensional space. All right, but if we have a given vector field F, and if we have a given closed curve gamma, then the circulation of our vector field about gamma is going to be defined by one integral, and the flux of our vector field across gamma is going to be defined in terms of this other integral. And so let's take a look at these integrals and try to make sense of what they are saying. So maybe first, I'll point out that the integral sign here, we have our gamma indicated down here so that this is integrating over gamma. So gamma is our domain, and we are once again looking at a line integral with a curve as our domain. So it's integrating over gamma. You'll also notice this little circle that's put over here on the integral sign. This is standard notation if the curve that we're integrating over is a closed curve. So this is just saying that gamma is a closed curve, and we are integrating over the entire closed curve. So that is the sort of notational framework that we see here. And then you'll notice the actual integral that we compute is our vector field F dotted with this other vector field T. And so this other vector field T, well, this is going to be our unit tangent vector after we parameterize. And so let's try to sketch this out. We have a given vector field F, which I'll sort of draw over here in our schematic in red. So let's say that our vector field, maybe it kind of looks like this. And then in the background of this vector field, we have this closed curve gamma. Now, once we parameterize gamma, we're going to introduce this parameter t. We're going to give it an expression x of t, as t ranges from a to b. And then along that, we can compute a velocity vector and a speed, and then we can divide the velocity vector by the speed to get our unit tangent vector. So all of these little blue vectors here are the unit tangent vectors. They are tangent to the curve, and they have unit length. And so you'll notice at any given point on the curve, we can look both at the red vector field vector, that's our F vector, and we can look at the unit tangent vector, that's our blue vector. We can calculate their dot product, And we can do that at every single point on the curve and then integrate up around the curve. And that is what the circulation will be. Very quickly, I'll jump down to flux. The flux of a vector field across a closed curve is defined pretty similarly, except instead of a unit tangent vector, we're going to be looking at the so-called unit normal vector. Right? And so this is the vector that is not tangent to the curve, but is in fact perpendicular to the curve. So if I have a similar simple closed curve, I could go and calculate the unit normal vector in a slightly more complicated way than the unit tangent vector, but we'll talk about that. But we'll get this unit normal vector is going to be completely perpendicular to the curve. But again, at each point on the curve, we can calculate our red vector f, our blue unit normal vector n, take their dot product, and then integrate up that quantity over the entire vector field. And so I'll make this remark that even though we are dealing with a vector field f, we have this dot product that's occurring, f dot t for circulation and f dot n for flux. And once we perform this dot product, the end result is no longer a vector quantity, but a scalar quantity. And so both the circulation and the flux in practice are actually scalar line integrals, right? They are scalar quantities that we're integrating up over this curve. So they are scalar line integrals. All right. So those are going to be our definitions and our framework. You'll notice in order to actually compute the circulation or the flux, we will need to go through the process of calculating or choosing a parameterization for gamma. From that, calculating our unit tangent vector and or unit normal vector, and then, performing the appropriate integration to get our answer using our scalar line integral equation from before. All right. And so with all of that, let's look at an example. I was going to say before that, I just want to note, because this is a scalar line integral that we'll end up with, right? The scalar line integral formula, it's going to be an integral as t goes from a to b. We're going to have our scalar function. So this is the piece that is inside the parentheses. This is the f dot t, but calculated, or f dot n, but calculated as a scalar quantity. And then just as a reminder, at the very end here, we will need our x prime of t dt. So that is our formula for a scalar line integral, and we'll be using that for both circulation and flux. Okay, so with all of that, let's actually get into an example here. Let's calculate the circulation and the flux of the vector field x comma y. So this is our vector field f here. And our gamma is going to be the circle of radius 2. So over here on the right, you can see the picture that we've drawn. Our vector field f is the vector field that is radially moving away from the origin. And so as we get further out, our arrows will get bigger and bigger as our x's and y's are larger. So that's going to be our vector field. And what you also see is the circle of radius 2, and that's our gamma, drawn there as well. So I'll highlight that right here. And so because this is a closed curve in two-dimensional space, we can calculate the circulation and the flux. And so let's give this a try. The first thing that we're going to need to do is we're going to need to actually parameterize gamma. And let's do this using our maybe most standard parameterization. X of t equals, and now this was a circle, so we're going to use cosine and sine. It's a circle of radius 2, so let's call it 2 cosine and 2 sine. So we'll get 2 cosine of t, 2 sine of t, and this parameterization is going as t ranges from 0 to 2 pi. We have to go up to 2 pi to complete the circle and make this a true closed curve. So that is going to be our gamma. And now let me actually front load, before we actually get to the calculation of circulation and flux, let me front load some of the unit tangent and unit normal calculations. So let's quickly compute x prime of t is just going to be negative 2 sine, comma 2 cosine. And then the speed of that, so the norm of the velocity vector, right, is going to be the dot product of that with itself. That's going to be 2 sine quantity squared plus 2 cosine quantity squared, and then the square root of all of that. So we'll get the square root of 4, and we will get 2 as our answer. So we're tracing this out at speed 2. And this means our unit tangent vector is going to be the velocity divided by the speed. So we're going to divide by the number 2, and we'll just be left with negative, 2, but then divided by 2. So just negative 1 sine of t, comma, cosine of t. Perfect. And that will be our unit tangent vector. And looking at the picture on the right, if I were to draw that out, we would get all of these unit tangent vectors going around in the direction of our parameterization with unit length. All right, but how do we use this to calculate the normal vector, the unit normal vector? Well, in two-dimensional space, this is relatively straightforward. We can just use a little trick. In short, the unit normal vector that we want is going to be the unit tangent vector rotated 90 degrees to the right. So if we had our unit tangent vector from before, rotating it 90 degrees should give us our unit normal vector. So we'll get something that kind of looks like this. And I recognize now this picture is getting a little bit messy, but you get the idea here. Okay, so we want to rotate this 90 degrees, but how exactly do we do this systematically? Well, I will say that if we're in two-dimensional space and our unit tangent vector has the shape of a comma b, so it has some quantity to it with an x coordinate or an x direction a and a y direction b, then the unit normal vector can be found by rotating 90 degrees, and that ends up giving us a b, comma, minus a. So we flip the location of the a and the b, and we add a negative sign to that second component, and that gives us the normal vector. And let's just confirm this, right? I'm just sort of pulling this out of thin air, but let's confirm. Just do a quick little calculation down here. When t equals ... we can say n equals ... And so let's just try a few of these. So when our unit tangent vector is the vector 0, 1, as it is in this very first case right here. So that vector pointing straight up is the vector 0, 1. So when t is 0, 1, n is the vector 1, 0. And we see indeed that that would be the case here, sort of pointing straight out like that. Similarly, when t is the vector, let's say, -1, 0. So if we're up here at this very top point of the circle, our vector is going to be, our unit tangent vector is going to be -1, 0, pointing straight to the right. Our normal vector will be 0, comma, and then -1. So we'll get 0, +1. And indeed, at that point, our unit normal vector will be pointing straight up in the 0, 1 direction. So, 2 examples does not make a proof, but you'll see that every time we have a unit tangent vector that's of the form a comma b, then the normal vector can be computed by flipping the position of a and b and flipping the sign on the a quantity, making it negative. And now, what does that mean for our specific unit normal vector? Well, if our unit tangent vector was negative sine comma cosine, our unit normal vector, all of those blue vectors that you see sketched in the image, will be cosine comma negative sine. So in other words, we just get cosine of t comma positive sine of t. And I'm going to erase that positive. I think it looks a little bit too much like a t. But yeah, so we get cosine of t comma sine of t as our answer. So all of this is being done without any thought about the specific red vector field, capital F, that we are looking at in this problem. We're just calculating circulation and, we're calculating all of these quantities involving our curve. But now let's return to the world of line integrals and specifically circulation and flux. So we have our gamma and we have our capital F. And so let's return to calculating circulation. From our previous problem, or from what we've seen, this will be the integral over the closed curve gamma of f dotted with t ds. That's a scalar line integral after the dot product is computed. And so that means that we will need to compute an integral as t goes from 0 to 2 pi. And now let's plug everything in. At time t, f of x of t, well, our vector field was just x comma y. So x of t, f of x of t, is just going to be 2 cosine of t, comma 2 sine of t. So we get 2 cos t, comma 2 sine t, and then we're going to dot that with the unit tangent vector. So that's our negative sine of t, comma cosine of t. And then, because this is a scalar line integral, we're going to multiply by x prime of t. We're going to multiply by the speed, which I guess in this case is just 2. So we'll multiply by 2 dt. But now notice when we go to set up this integral, we have to compute the dot product. So we get 2 cos t times negative sine t. So that's negative 2 cos t sine t plus, and then it's 2 sine t times cos t. So 2 sine t cos t. All of this is multiplied by 2, but as you can see, that doesn't matter. The negative 2 cos t sine t and the positive 2 sine t cos t will cancel each other out. So this will just be the integral of 0 dt, and we get 0 as our answer. So the circulation of this vector field around this curve is 0. Now, how about the flux? The flux is a very similar computation, but instead of f dot t, it's going to be f dot n ds. And so, very briefly, that should give us the integral from 0 to 2 pi. We start off exactly the same way. F of x of t was 2 cos t, 2 sine t. But then we're going to dot that, not with negative sine comma cosine, which is what we had for our unit tangent vector, but instead for cos t sine t for our unit normal vector. We're then going to multiply at the end. Sorry, that's not a dot product. That should be a multiply. We're going to multiply by the speed of the parameterization. So that's times 2. And then integrate dt. Okay, and let's do some creative moving things around here to try to save some space. Just slide that off the screen, I guess. But that's okay. When we do the dot product here, we'll get 2 cos t times cos t plus 2 sine t times sine t. So notice that will become 2 cosine squared plus sine squared. So we'll just get a 2 that pops out. And then we're going to multiply by that final speed of 2. And so we're integrating just the quantity 4 from 0 to 2 pi. And so we're just going to get 8 pi as our answer. And we can conclude that the flux across this curve is equal to 8 pi. Now, just to close, let's talk briefly about what circulation and flux are measuring. If we think about our vector field as describing a type of fluid flow, so either the flow of a liquid or the flow of a gas, then the circulation tells us as we go around our curve how much this vector field is contributing to that path. So the circulation is telling us how much our vector field is contributing to our little particle as it circles around the simple closed curve, around the closed curve. So the fact that our answer was 0 here indicates that the circulation around the path, around the curve, does not actually interact with or is not actually guided by the vector field in question. And as we look at this vector field, we see that all of the arrows are perpendicular to the curve itself. And so as our little particle travels around the curve, it really doesn't ever move in the direction of those red arrows. It's always moving in a perpendicular direction to those arrows. Now, the flux, on the other hand, is telling us the opposite. It's not telling us about how the particle moves around the curve. It is telling us about how the fluid moves across the barrier of that curve. So how it moves from the inside to the outside. And what we see here is that there's actually a lot of movement from one side of the curve to the other, right? Looking at the red vector field, all of our fluid is basically moving across that curve, across that membrane to the other side. And so under that interpretation, there's actually a great amount of fluid that is moving across this boundary, and the flux is the integral that captures that. So when we get an integral of 8 pi, that is telling us that a certain amount of fluid is flowing across the boundary of this region from the inside to the outside, and we see that in the red arrows here. So these are two very specific kinds of line integrals, both scalar line integrals, but that are calculated using vector field quantities, the circulation and flux. Both of these have applications in physics and engineering, and through some clever interpretation, they can push forward our mathematical theory as well. So all of that and more coming up later. But thank you all so much for watching, and see you next time.